This is topic 4.4, 4.3, and 4.7 from the course and exam description for AP Environmental Science. Make sure you follow along with the learning targets and your study guide. All right, so there's a word to know called insolation. It's basically solar radiation, which is the sun's main source of energy. And then we have sun coming in and solar energy and heat and all that stuff. And then heat is distributed from the main area where it hits, which is the equator, to the other parts of the earth through atmospheric currents and oceanic currents as well. There are two main reasons why the equator is hotter than the poles. First, you have the curve of the earth. So take a look at this picture here. The curve of the earth is less of an angle here at the equator, and so you have more radiation per surface area. Now take a look here in the temperate zone. I live in the temperate zone in Southern California. The same amount of solar radiation is spread out on more land, and so it's diluted. So you have less solar radiation per square foot. And then we're also going to talk about the tilt in a second. So let's go on and take a look first at our latitudes. So this is a reminder of what our latitudes are that you should have learned in another science class, but a lot of times students forget. You need to know that the equator is 0 latitude, and then it goes up to 90 north latitude at the North Pole and 90 south latitude at the South Pole. You have the tropical regions between the Tropic of Cancer and Tropic of Capricorn. Then you have the temperate regions. I live in the temperate region in Southern California. Most of the United States is temperate. And then maybe Alaska might be, the top of Alaska might be in the polar regions. So the areas surrounding the North and the South Pole. We have our northern hemisphere above the equator, our southern hemisphere below the equator. All right, another term to know that you may have learned in another class, for example, chemistry class when you learned about climate change. There's a term called albedo, which is the reflection of solar radiation off the Earth. All right, so let's talk about seasons on the planet. So one of the reasons we just talked about why some areas are hotter than others is because of the curve of the Earth. But then also there's the tilt. So the Earth is tilted on its axis, 23.5 degrees on its axis. So the Earth is slanted. And that means that we have seasons because of that. So in the northern hemisphere where we live, when it's tilted toward the sun, and half the year, remember the Earth travels around the sun one time per year, 365 point something days. It travels around the around the sun one time a year. Then it spins on its axis every 24 hours. That's why you have day and night. But the reason why you have seasons is because it's traveling around the sun and it's tilted either toward the sun and then it travels around to the other side and is tilted away. The Earth itself doesn't move like this. It doesn't do this. The Earth's tilt stays the same and it travels toward the sun and away from the sun. So we're not talking about being closer or further away from the sun. That's wrong. If you write on a free response question, and I graded these nationally a few years ago, it was explaining why there's seasons. And if kids put, well, it's summer when the Earth is closer to the sun, is wrong. So that's completely wrong. You say it's summer when the tilt of the Earth if you're in the northern hemisphere, for example, and you're tilted toward the sun half the year, for a few months, 3 months of the year, that's summertime. And then as you move around the sun, you're tilted away, and that's wintertime. So the tilt of the Earth brings you more direct solar radiation, and that is the term you want to use. You want more direct solar radiation. You do not want that it's closer or further from the sun because the Earth stays the same distance from the sun. Your tilt means you're tilted toward with more direct solar radiation or tilted away. And when you're tilted away, that's winter. Okay, we have our seasons here. It's really important. I'm not going to read all of the captions here, but you need to pause your video so that you can examine what this is like for the Northern Hemisphere in June. So the June solstice would be June 21st to 22nd, and that's the longest day of the year for the Northern Hemisphere. And then it's the shortest day. Now, when we say day, we're talking about daylight hours because a day is 24 hours. But when people say it's the shortest day, it means it has the most sunshine and hours of sun versus night. And so in the Northern Hemisphere, that day is in June, but it's opposite. So if you lived in Australia, June would be your winter and it would be the shortest daylight hours of the year. And so the Northern Hemisphere and the Southern Hemisphere have opposite seasons. For example, if you lived in Australia, Christmas is still December 25th, but that's summer. It's summer vacation. You're going to have a pool party because it's summer. Kind of weird to think about. All right, going on. All right, so here's a couple of little questions to review. Which location experiences 24 hours of daylight on December 21st, the South Pole? So they're opposite of us. So on June 21st is our shortest day of the year. And if you're at the North Pole, there's no sun that day. Now, we don't live at the poles. So on our shortest day of the year, we're still going to have sunshine here in California, but less hours of it, the least amount. All right, so again, take a look at these questions. Start to think about and wrap this through your head. The North Pole receives 24 hours of daylight June 21st. The equator receives the most solar radiation. And then we talked about this earlier. The heat is distributed from the equator to the poles by oceanic and atmospheric currents. All right, you also need to know that nitrogen makes up most of the atmosphere at 78%, and oxygen is about 21%. The other gases are found in very small amounts, but our greenhouse gases like CO2 and methane, even though they're found in small amounts, comparatively, they pack a big punch. We'll study that later this year. All right, you do need to know the layers of the atmosphere in order. And so down here at the surface of the Earth, we have the troposphere, then the stratosphere, then the mesosphere, then the thermosphere, then the exosphere. Now let's talk about the details you need to know on the next slide. But real quick, you do not need to know the kilometers. Okay, that is not something you need to memorize. You do need to memorize the order, however, and a few details about each. Okay, so where we are is the thermosphere. That's where weather is. It's where climate is. It travels up to, just below 20 kilometers. So it's very high above us. Our airplane rides are usually in the troposphere, maybe a little bit in the stratosphere for a long haul flight, but we're really spending, our time in the thermosphere. I laugh because my students sometimes go to Las Vegas and there's a casino hotel there called the Stratosphere, and it's super tall, but it is not in the stratosphere because, things at Vegas are fake. It's not the real Eiffel Tower. It's not the real Statue of Liberty. It's not really in the stratosphere. Okay, you do need to know, however, in the stratosphere is where you have the ozone layer, which protects us from UV rays that can cause skin cancer. Okay, what you need to know about the mesosphere is not much. Meteors burn up. I've actually never seen that question on the AP test, so you may not need to memorize really anything as far as I'm concerned for my tests on the mesosphere. Thermosphere also doesn't have much. Satellites will appear in the thermosphere and the exosphere. You'll also see the northern lights in the thermosphere. All right, so air. Let's talk about atmosphere and air properties. Air has four main properties: the density, water vapor capacity, adiabatic heating and cooling, Latin heat release. Now, there's a lot of terms here you don't need to know for my test or the AP test, but it helps explain some things that you do need to know. So you do need to know density is mass over volume. You've been learning that in science classes for a lot of years. That should not be new or a surprise. You do need to know about water vapor. It's the amount of water held in the atmosphere. So if you're in a very humid place, there's a lot of moisture in the air. And the maximum amount of moisture is the saturation point. So here's a graph about that. At certain temperatures, water can hold a certain amount of moisture before it has to release that moisture and it rains. So you don't have to memorize anything here, but you do need to be able to read a graph like this. Oh, at a certain temperature, the saturation point is this many grams of water per meter cubed. So at 40 degrees, it can hold this amount of water before it has to drop that moisture in precipitation. Okay, now here's a lot of technical stuff about why cold air rises and, I'm sorry, back that up. Warm air rises and cool air falls. And it has to do with things about adiabatic cooling and latent heat release. I'm going to simplify it a little bit for you on the next slide. But if you want to know the ins and outs of how this weather works, read this slide, pause the video, read this slide. But for our purposes in APES, you don't have to know the ins and the outs of this process. But let's look at the next slide and let's see what you do have to know. You do need to know that warm, wet air rises. And as it rises, the cold air cannot hold as much moisture, and it has to drop it in the form of rain. So you need to know that warm air rises, and it often holds water from evaporation when it's summer or not even summer, it still evaporates. And from trees transpiration will evaporate or transpire water into the atmosphere. That warm water and warm air rises, but then when it gets to the upper atmosphere and it cools down, it will rain. It will condense into clouds, it will rain. And then the cold, dry air falls. And so again, those terms in there, adiabatic heating, latent heat release, you don't have to know those vocab words. You just need to understand that warm, wet air rises, cools, drops its moisture, and cold air falls. And it does this over and over again. This is called a convection current. This happens in the atmosphere. It happens in the ocean with water. It happens in the magma with It happens in the, asthenosphere with the magma. And that's what drives plate tectonics. All right, so here's another diagram. We have this warm air rises, cool air falls all throughout the globe. Now, when it surrounds the equator, we call them Hadley cells. And so that's the equator to 30 degrees north and 30 degrees south latitude. At 30 degrees north and south latitude, it's dropping drier air, which is one of the reasons why deserts are often found at 30 degrees north in latitude. For example, I live at 34 degrees north latitude. I live in the chaparral. It's a dry climate. It's not quite the desert, but it's dry. And part of the reason why it's dry is because of convection currents in the Hadley cells. And if you go a little bit further east from me, I'm not in the chaparral shrubland anymore. A little bit east of where I live is the Mojave Desert. So now we are in true deserts. Now, it's a pattern, it's not a rule, because if you go across to the eastern United States and you're in the 30 degrees latitude, you're like in South Carolina, North Carolina, you are not in desert there. So it's a trend, it's not an absolute rule, but most deserts are found at 30 degrees, around 30 degrees north and south latitude due to convection currents. The other two currents are called the polar cells, which surround the North and South Pole, and the feral cells, which go from 30 degrees to 60 degrees North and South latitude. So you do need to know that. You need to know the polar cells, then the feral cells, then the Hadley cells. So Hadley surround the equator, feral is in between, polar surrounds the poles. All right, so the rising and the falling of air in convection cells, that air is diverted because of the spin of the Earth. So the Earth spins around its axis once per 24 hours. So the Earth is actually spinning pretty fast. It has to spin faster at the equator because there's more of the Earth at the equator. So if you take the circumference of the Earth at the equator, it's a lot more than the circumference of the Earth at the poles. So it has to spin faster to go around once every 24 hours. The poles have to spin slower to make that same rotation in 24 hours. If that doesn't make sense, stop and think about it for a second, and then it might make sense. Okay, that spin of the Earth is the Coriolis effect, is the deflection of this air which causes winds. And so the Coriolis effect will deflect those winds, that air created by convection currents. So if you're asked about what causes winds on the AP test or my test, you'd say it's convection currents, the rising and falling of air, plus the spin of the Earth with the Coriolis effect creates winds. And deflection occurs faster or slower or more or less because of the distance at the equator versus the north and south poles. Oh, and here's a great diagram to show that. So at the equator, it has to travel faster because it has more distance to cover in one spin than the 30 degrees north or 80 degrees north. All right, so Coriolis explains our wind patterns and how they deflect. Now, wind is deflected to the to the right in the northern hemisphere, to the left in the southern, and it depends on where that wind or that air started from. So, for example, if you see this red arrow, you're like, oh, well, these are being deflected to the left, but that's the northern hemisphere. It doesn't make sense. Now, if you look at the globe from up above, and the wind started from the north and is heading south, it's actually deflecting to the right because of where it starts. And if you look at the globe down, now you'll do a lab on the Coriolis effect that will help you understand with a blow-up beach ball so you can see these patterns a little bit better and have it make more sense. All right, last slide. So we're going to talk about these wind patterns here, and know that if winds are coming from from the ocean to land, they pick up moisture from evaporating water and bring rain to that location. If winds come from land, they're going to be drier. So warm ocean currents typically evaporate more and bring more rain to the land than cold currents. Okay, so here's an example question at location 2. Would the weather in January be hot or cold? So let's look at 2. Look at the wind. See this arrow here? It's coming from land to this location. It's on the equator. It's going to be hot. It's going to be dry. So it doesn't matter if it's January or not because it's the equator, so it's going to be hot. And it's going to be dry because it's coming from land to this location. So it's going to be hot and it's dry due to its wind patterns. So those are the kinds of things. What would be happening at number 4 in January versus December? At location 1, January versus December. So you have to think about your seasons, whether it's hot or cold. You have to think about, is it coming from the ocean? Is it coming from land? And so you don't have to memorize all these things. You just need to be able to take what you've learned in this presentation and on your notes and figure out, oh, look, location 3, it's coming from the ocean. So it's going to carry wet. So the air is going to be wet at location 3. And this is January, so it's coming from here, and January is summer in the southern hemisphere, so it's going to be warm coming from the water to location 3. It's going to be warm and wet. That's the kind of thing to figure out from these types of problems. All right, that's it for these 3 sections.